this weight vector is primitive, meaning it doesn't have any multiple. And also, let me assume, without loss of generality, that this sum of AI is non-negative. From 1 to n. So if we consider the GIT quotients of this problem,
so the AIs are integers or complex number?
AIs are integers.
Okay.
Non-zero integers. Yeah. So the GIT quotients are generally of, there are two possibilities. So let me recall for you that to do a GIT quotient, we need to choose a ample equivariant ample line bundle. Since here we are Cn, we only need to choose a character of C star. Here. Choice of C star character. So there will be two possible quotients.
Non-zero character.
Yeah, thank you. Okay. Non-zero character. So there will be two possibilities, but I tend to think in terms of symplectic geometry. So I would want to view this as a Hamiltonian reduction of S1 acting on Cn, where the Hamiltonian function h Z1 through Zn is going to be AI and Zi squared. So the two quotients, let me denote by x plus and x minus. So x plus will be, say, h inverse some positive number, and then quotient by S1, and x minus be quotient by S1. As written, it's not precisely correct because I didn't tell you what happens if there are singularity in the quotient. So let me rewrite this also as a GIT quotient, where I will define the unstable locus for the plus side and the minus side. So the plus side for Cn, it will be removing the part where all the positive AI corresponding Zi being 0 simultaneously, where for all I such that AI are positive. So those are the unstable loci for the plus quotient. So once I remove that, I can do the C star quotient. Similarly, I can do this. All I with AI less than there. So the thing one end up with will be an orbifold. So I will consider the so-called stacky GIT quotients. So these are going to be smooth Dilley-Mumford stack. Just okay. So so are there any questions so far? Okay. So we have these kinds of two quotients, and we can apply mirror symmetry, homological mirror symmetry to them. And one way of doing homological mirror symmetry is to use constructible sheaves. So there is mirror symmetry with mirror given by constructible sheaves on torus. In particular, we would have a lambda plus sitting inside T star of Tn minus 1, a conical Lagrangian. And let's say maybe lambda plus and the lambda minus. And we would have the coherent sheaves on the stack, by which I really just mean C star equivariant sheaves on that semi-stable part of the Cn. This would be equivalent to constructible sheaves of lambda plus on Tn minus 1, and the similar result for x minus. Okay, so all these are just given to us by the coherent constructible correspondence. I perhaps should put a W here to mean it's so-called wrapped constructible sheaves, which I will explain later in more detail. So these are using coherent constructible correspondence due to, well, let's say originally due to Bondal providing the idea, then developed by F.L. Fang and Bohan Fang, Melissa Liu, Truman Zaslow, and then Kuwagaki. There are many people I omitted, and then finally, the final form we use here is due to Kuwagaki. So that seems to be a satisfactory story. So what do I have to add here? What I want to say is I want to describe the relation between the x plus and x minus. So there is a semi-orthogonal decomposition of the coherent sheaf categories. So let say eta equals to the total sum of AI. And let's say, depending on eta being positive or 0, we assume it's non-negative. So if eta equals to 0, we have equivalence of categories. And if eta is positive, then there is a semi-orthogonal decomposition of x plus, which is a bigger guy. And then let me write it schematically as the following. So the vector represent the category of just a vector space. Or you can think these are represented, these vectors are just some exceptional object. And then,
can I ask a question?
Yes.
I just want to make sure that on an A side, when you have constructible sheaves, this is just the covering of the pair of pens, right?
I'm not sure whether I understand the question. The covering of pair of pens.
I mean, if your A's were just the basis vectors, I mean all A's are kind of ones, then you would just have a pair of pens.
Yeah, let me think. If the A's are just say 1, 1, 1, then what I get would be first of all, the x minus would be empty, and the lambda minus would be empty, and then x plus would be say removing some part, and this will be P2. So lambda plus would be something in over in T star T2. It's like this.
So this is not pair of pens. This is really like the cotangent bundle of the torus.
Yeah. Yes.
Okay. Sorry. Okay. Thanks.
Yeah. That's nice. I have the chance to talk about one particular example. Yeah. So we have we have all the story worked out. On the B side, we have either semi-orthogonal decomposition or equivalence of category. This is due to Daniel Halpern-Lessner, I call DHL, or Matthew Ballard, David Favreau, and Katsarkov. However, on the A side of the story, the A side story has been worked out by Gabe like 4 years ago. So here I'm proposing to give another solution to a description to the A side. So let me write that down. The mirror to the above A side mirror to the above semi-orthogonal decomposition has been worked out by Gabe Kerr using the traditional Kayas et al. Category. Kayas et al. And we're still trying to understand that. And today I want to just, as I mentioned, use a different A model. A model description using the sheaf description. So the trouble is the following. You see, we automatically get by those we automatically get these well, sorry, my notations not consistent. I tend to think these skeletons determines everything, so I tend to write just a sheaf of the skeleton. We obtain using the coherent constructible correspondence automatically this semi-orthogonal decomposition. But I want to start purely from the A side without the help of the B side known result and without the help of coherent constructible correspondence. I want to be able to see how to relate this category and this category. So the goal or the question is to understand this semi-orthogonal decomposition purely using constructible sheaves. Purely using constructible sheaves. So the solution, roughly speaking, is a cobordism between lambda plus and the lambda minus. Cobordism.
So the constructible sheaf is on the lambda plus minuses or on the x plus minus?
The constructible sheaf is on the torus on the Tn-1.
Okay.
And it has certain singular support condition determined by the skeleton lambda. But if you wish, you can also forget about the Tn-1, just to remember the skeleton and its thickening. So that also determines the category. So in certain sense, the skeleton is the more fundamental object. Construct a cobordism between lambda plus and lambda minus. So what we end up having is that if eta equal to 0, then we have a family of categories. Cobordism, let me denote that by a lambda sub t. So lambda sub t in the same space. Then this family of categories indexed by t, let's say maybe t is in 0, 1, are all equivalent. So we have a fixed ambient space, T star Tn-1, the cotangent bundle of the torus, and we have a moving skeleton going from lambda plus to lambda minus, or maybe going from lambda minus to lambda plus. If eta is positive, then as lambda t changes, there will be eta many moments where the category jumps. Lambda t jumps. And we can precisely describe those jumps and those matches with the semi-orthogonal components in the plus side. So that is basically the result I have. And maybe a remark is that this interpolation, this cobordism, are purely not built by hand. It's given to me. Is there a question? Okay. Comes from something called a window subcategory. Cobordism. Window subcategory. So it's like, well, I said previously, I do not want to borrow from the B side computation, but actually I cheated. This lambda t, this family of skeletons, their construction are inspired by the window subcategory on the B side. So in particular, lambda t arises as a lambda w restricted to t, where lambda w is a skeleton of a one-dimensional Haier space with an actual R parameter, and I'm restricting it to the slice T here. And W stands for window. Okay.
Could I ask a question?
Yeah.
Does this make sense at the singular time? As in when T passes through
Yeah.
the...
So yeah, when T passes through the singular time, it has a sort of a semi-continuity. As T increases from, say, minus infinity to positive infinity, what will happen is that there are certain singular times, say T1, T2, T eta, and the sheaf at lambda Ti is equivalent to sheaf of lambda Ti minus epsilon. Wow. Yeah, so those things do make sense, but it doesn't make sense in an interesting way. Yeah.
Thanks.
Mm-hmm. Okay. So maybe let me give you one example of how things works. Or maybe I guess maybe to give the example, I maybe have to explain some terminology about constructible sheaves and the coherent constructible correspondence. But anyway, maybe let me give you the example first, and then I will explain. So example. So I'll give you three, maybe two examples. Say star acting on C2 with weight 1 minus 1. So in this case, the x plus and x minus, they are trivially equivalent. And I also want to show that the lambda plus and lambda minus, what do they look like? So the lambda plus is sitting inside the cotangent bundle of the S1. So this is the T star S1, and this let me use a different color, is the zero section union with the cotangent fiber over a point. So this similarly, lambda minus is the same picture. But it might be interesting to look at what is lambda W. Even in this case, lambda W is not trivial. Lambda W is living inside T star T cross R. It's hard to draw on a cylinder, so I would like to unwrap the cylinder to a plane. So I will draw T tilde inside T star R cross R. It looks like the following. So here's R2, and I'm going to draw something going off in 45 degree, like that. And because it's periodic, I should draw this thing that's periodic in one direction. So I should draw something living in T star R2, but I can only draw its projection on the base R2. I will indicate using the hairs what's the conormal directions I'm having. So it's something like this. Okay. So when you wrap up on the vertical direction, you end up with a cylinder, and you have something like this. Okay. So if you take a slice, so here's like 0. So if you take a slice in the middle, here's like say at t equals to 1, you end up with a circle, and together where the skeleton intersect the slice, you end up with a sort of a vertical part. So lambda say plus would be obtained from the window skeleton by taking a slice.
Hey, is the red skeleton, is that have both directions, or is it just have one direction?
Oh, thank you. You're right. I was wrong. Of course, only should have a single direction, and also this. So that's how the window skeleton looks like in this trivial case. It's
when you cut at 0, do you have
yes.
to make a choice, like which side you're on? Or
it doesn't matter if you cut at 0.
Yeah.
So I haven't tell you how to compute the restriction of a window skeleton to a slice. But it's just basically these hairs define some half space locally, and you just use those half space to define the choice of half space on the slice.
Okay.
Yeah, so as I appeal to your intuition to see there's no ambiguity. It doesn't matter whether you approach it on the left or on the right. Maybe after that, maybe it's possible to consider this case where act on C2 with weight 2 and -1. So I will just draw the window skeleton without much explanation, and I will revisit this example later. So the skeleton looks like the following. So I will have to draw it with the help of grid. Okay, very convenient. So previously it's 45-degree. Now I will make them upright. And previously the vertical projection direction now is the map of mu xy equals to 2x minus y. So the projection direction is a vertical line that's passing through this point. So imagine you are projecting R2 along, collapsing this dashed line. So we're going to draw these periodic objects, and then we're going to draw another copy of this periodic object. Let me use maybe a different color. Okay. So I will now decorate these things with hairs. So if you wrap it up along this this direction, you end up with something on the cylinder looks like the following. Let me think. Yeah. And this exit here and it comes back here. And this goes like here. So you can see that the transition happens automatically, where if you have a time equals 1, so the lambda plus, looking at this slice, is going to be a circle with two stop like this. So if you draw it, so this is a projection image. So if you draw it in the T star S1, it looks like that. Okay, so it's basically a circle with 2 points where there is like a half conormal standing over those 2 points. And if you look at here, you end up with a lambda minus a circle with just a one stop at over 1 point. So this corresponds to x plus being C mod Z2, and x minus is just being C. And we can observe that how does the skeleton change as we change the slice. If you try to move the slice from right to left, we will see that initially these two stop will move at the same pace to the right or to the left. And then after it passes through this moment, one of the stop tries to move in the opposite direction, and then they will collide at this moment, and they will merge into one. So that's the movie or the isotopy of the skeleton. So maybe that doesn't seem to be too interesting, but the other examples I perhaps cannot draw for you. I will show you some pictures. So here's the draft of the paper. So hope you guys can see here. But maybe you can't see my hand. So this example, where is a 3-dimensional example, the quotient will be 2-dimension, and the bottom 3 picture represents the slice picture. Okay, so the middle guy is something in between. So on the left, you have something leaving over the corner. On the right, you have something additional, the bottom and the top component of the skeleton is in addition to the lambda minus. Okay. Okay, maybe I've confused you guys enough with all these hairs and lines. I want to maybe to pay back. I want to maybe introduce a bit about the notation about the constructible sheaves, singular support, and more importantly, what do I mean by deformation of skeleton?
Can I ask what's in the 1-1 case for the P1? What's the story? What's the window thing on?
In the P1 case, right? So in the P1 case, we can also draw the window it will be it will look like the following. So we have the dashed line being running like this way. So you end up with a cylinder if you quotient along the dashed line in like this. So it is the skeleton in this case does not cover the entire cylinder, the T cross R. It will be empty here. It will start to occupy stuff at this moment, and then it have hairs like this. So basically, yeah. So basically, you have two objects generating that skeleton. Is a union of, say, lambda 0 union lambda 1. Lambda 0 is the is a singular support like this, and lambda 1 is its shift like a little bit down here. Sorry, I can't really draw the picture. Sorry. So basically, it's a union of two objects, and these two objects should be considered as the line bundles O0 and O1 on P1. And I should say like it's not technically correct O0 O1, because if you identify P1 with the sheaves on the slice here, then maybe these two objects are O0 and O1. But if you shift that slice by one amount here, then the O0 and O1 will become O1 and O2. So you move your slice that will correspond to tensor by that ample line bundle on the toric manifold. Okay, close it. I don't know if that answers your question here.
Yes, thank you.
Okay, so maybe I plan to use the remaining time to give some terminology. So and then I want to discuss the notion of isotopy of skeleton, because I feel that's sort of the main valuable thing in this exercise. Because in general, when one builds a functor between two categories, a natural way to do it is to use a maybe build a kernel in the product using some Fourier Mukai technique. This sort of Lagrangian deformation of Lagrangians is like you want to have a continuous family of categories, and you want to use some monodromy or some and in the parameter space there may be some jumps, and you can try to follow a path in the parameter space and record the jumps, and that induces a category, a functor on those categories. So it's like a parallel transport. It's not quite parallel transport because it's not equivalence. Yeah, so that I think that maybe is an idea that can be used in other scenarios. This family of categories and parallel transport among them. So in this case, this parameter family is just R, and one can imagine a higher dimensional base. if you have, say, for example, C star to the k acting on C to the n, then there will be like a k-dimensional base. So maybe here I want to do certain review of constructible sheaves. So let's say so say M is, say, a smooth manifold, and suppose we have a stratification, a Whitney stratification. It just means that all these S alpha, they are smooth submanifold, and there are certain locally finite conditions. So they're just a nice strata. And the boundary or the closure of this can be written as a certain collections of strata. And we say a sheaf is constructible sheaf. Constructible if the restriction of the sheaf or constructible sheaf is constructible if exists a stratification. This is S alpha, such that the restriction is locally constant. Okay. And I want to maybe abuse terminology. I want to say a complex of sheaves are also sheaves. So usually denoted F is constructible if the cohomology of those sheaves are constructible sheaves themselves. So really, when I say a sheaf, it possibly means the DG category of cohomologically constructible sheaf. So so if S is a Whitney stratification, then you can consider this subcategory of sheaves where it's constructible with respect to S. So constructible with respect to this stratification. But then sometimes we want to have a better control of how things jumps. So we will define the singular support of F. So singular support of F is a conical Lagrangian. So I maybe so if a point in the cotangent bundle, let's say not in the zero section in the cotangent bundle, it is in well, let me be a little bit imprecise. It is in the singular support of F if around this point you can choose a small ball and choose a hyperplane with conormal C, and you have a ball here and this this sub ball, half ball, B minus. If the restriction map FB to FB minus is not a quasi-isomorphism, then this point is in the singular support of F. In general, you have to consider all those directions and then take the closure of those set to define what's a singular support. So given a conical Lagrangian, we can define the sheaf, the subcategory of sheaves on M. So with objects, so F such that singular support is contained in lambda. So it's a full subcategory with this condition on the singular support. Okay. So it is quite combinatorial, these constructible sheaves. So it has a combinatorial and computable nature. For example, on a real line, suppose your lambda is like this. So the zero section plus the positive conormal to 0, and then to well, maybe let me be more easy. Then the constructible sheaf on R with this stratification are represented as a representation of a quiver, because to give a sheaf on this guy, there are basically 3 possible open sets containing 0, open sets on the left and open set on the right, and there are morphisms among these sections. So if you denote A as say F minus 1, 1, B as F say minus 2, minus 1, C is F say 1, 2, then there are maps between these sections, or if you wish, stocks. So it's you can have A maps to B and C. So this is a so-called exit path category description for constructible sheaves. And say if M is R, but lambda is just half the ray, then I can represent lambda as an arrow sitting at this point. And then you still can represent, denote section over here as A, and section on the left as B, and section to the right as C. And you have these restriction maps. By the way, to see that we have restriction maps, you have to use the fact that F is locally constant. You can shrink this interval to be an interval here, and then you see it's indeed you have a restriction map. And so the hair pointing in this direction, that means if you restrict this guy to the right side, it should be a quasi-isomorphism. So the leg of a hair lambda here represents just you have essentially just a two stock to remember up to quasi-isomorphism. So usually we write this like a lambda like this, and then the stock have a map in this direction. It's against the hair. So it has a combinatorial nature that these constructible sheaves, It also has a symplectic nature, which is quite flexible. The reason is the following. If you have two family of sheaves, say FT and GT are family of sheaves, maybe indexed by T between say 0 and 1. So family of sheaves means they lives in they are slice of sheaves in a one hair dimension. Then one can ask when does how does the harm between FT and GT change? So there is a result like this. Harm of FT GT are constant in T if the singular support of FT at infinity is disjoint with the singular support of GT at infinity. So this infinity means I take the non-zero part of those conical Lagrangian. And so these are the Lagrangians sitting at in infinity. Okay, so we have a certain freedom in moving these sheaves without changing their harm. So that's something nice. And that should be compared with considering, morally speaking, it should be compared with harm of the Fukaya category. Okay, I'm no expert in Fukaya category, so I'm only just drawing some pictures. So you have, say, two Lagrangians, L1 and L2, in the cotangent bundle. Say there's T star of M, and you have L1 and L2. You are free to isotope them whatever you want using Hamiltonian isotopy, as long as their infinity part, their Lagrangian ends do not meet each other. Is invariant under deformation, Hamiltonian deformation. Are disjoint. Okay, so given this flexibility, one can try to build a certain categorical way of moving objects. So, so here is a result. I think if lambda is a conical Lagrangian, and lambda t, suppose it's a family of skeleton. Well, then one can ask, when does this family of categories remains invariant? Okay, so this remains invariant if and only if, well, we cannot say lambda t does not intersect with itself at infinity, but however, we can say something along that nature. It one can consider the contact space t infinity m subtract lambda t. if this family is of complements are contactomorphic on each other. So, so there's a way to test whether you can have equivalence of categories by deforming these lambda t's, and my result in this work gives you some example where you don't have invariance, but you can control how things jumps. So in this window category, window skeleton case, as you move through the window, taking slices, you will have a family of skeleton that are locally constant until you have certain jumps.
Is there a sorry? Is there
yeah.
So is this result passing through some notion of an equivalence with this partially wrapped category with this lambda t as a stop? Is this?
Yeah, it's it doesn't use the partially wrapped language. It's used purely sheaf language, but I think the idea is the same. Well, in the proof of the paper, there are two versions of the proof. One is a geometric version where one needs to consider some wrapping of objects. Wrapping of all objects, meaning deforming a sheaf so that its singular support are carefully controlled so that they do not touch a given Lagrangian skeleton. And in the limit, that sheaf has its singular support belongs into that Lagrangian skeleton. So there's some certain wrappings involved. So but that's
initially,
yeah.
Initially, in your earlier part of your talk, you had a W on these categories, like a wrapped sheaf, constructible sheaf category. Is this something that's necessary to put into this result here?
Yeah, yeah, it is necessary because in order to talk about coherent sheaf on the B side, you have to use the wrapped sheaf on the right.
Right.
Yeah, I've maybe forgot to adorn many of the places with W, but those non-characteristic deformation result is true whether you have the large constructible sheaf or the wrapped constructible sheaf.
Okay.
They're all correct.
Thank you.
Yeah, sorry, I don't have enough time to tell you the actual story about what's the window, but at least I show you some examples. So I think that might do. Okay. Let's see. So, other questions, I guess.
Sorry, I should ask that. So, well, thank you also very much for the talk.
Oh, that's it?
Thank you for your. I think it's 1 hour. Or...
Yeah. Well, I mean, you're
Okay,
welcome to continue.
I have a question, but
sure.
Go ahead, Jesse.
So, right. Let's just consider the balance case when like the sum of AI is equal to 0, right? In that case, we have a non-characteristic deformation.
Yes.
I mean, I'm just trying to link this with like what I have in mind, which is like in my case, like everything is equivariant. So basically, this transition is not really. I mean, I kind of see the transition as like as doing the following. So you have like some stop on one side, and you like artificially add like the other side, like you're artificially adding some linking disk supported on like the semi-stable skeleton from the other side, and then after that you do a stop removal, and that would give you the equivalence. But I don't know the same thing in your story.
Okay, in my story, there's no direct stop removal. I think what you are saying is following. You have a bigger skeleton where it contains some extra components.
Let's say like we're doing the 1, 1 minus 2 case, right? So we have like a 3-dimensional thing, and you're only looking at the like 2-dimensional facets, right? And you're taking like on one side you're taking 2 of them, and on the other side you're taking the other, like the third, right? And what I'm kind of doing is that, okay, so over at 0 you have some singular thing, and you're adding like this other piece in, and you like sort of like stop removal, so you remove like the, you know.
Yeah, that's a
that's kind of like the equivalence I get from this procedure, but I'm not exactly sure if you're getting.
Yeah, that should be equivalent. Yeah, yeah, you are. It's like you have a, how should I say, maybe glued together, say the left side with the right side to create some bigger, thicker skeleton in the middle, and then you use that to show the equivalence.
Yeah. Okay.
Other questions from the audience? I had a question. I don't know if I don't want to interrupt anyone else, but so you mentioned something at some point about on the higher, like a higher dimensional setting. So this is sort of these birational coordinates, is sort of really simple variation of GIT. But if I start with just a general toric variety, and then I can look over sort of the secondary fan.
Yeah.
Do you have a description of some universal skeleton like lying over the secondary fan? That's
right. Yeah. It's like every time. Yeah. Right. Let me give show some screen. Yeah. So actually, Jesse and I are working on a special case of that called the zonotope skeleton. So in general, there's no universal skeleton. I don't know how to construct that. So you're asking if I have C star K acting on C star N, and then there is some projection like this, and there's a projection of that moment polytope of Cn into Ck defines certain strata like that, certain chambers. In general, no universal skeleton, because to require a universal skeleton is the same as requiring a common window subcategory that maps surjectively. Let's say even in the equivalence case. So having a universal skeleton as long as it means you should have a certain window subcategory in the in say in quotient C star K, such that this GW under the restriction map, okay, for each chamber, right? You have a restriction map for each chamber. So C denotes the chamber. So such that you had an equivalence restriction window subcategory. But this may not exist. What you can do is, like, for each chamber, you build a window subcategory for that chamber. But as you go to different chamber, you end up with a different window subcategory. So that's usually the case. You can't make one subcategory does everything for you. There's, of course, on the other hand, there is a special case of I don't know. I what special is. Yeah.
I would have thought these window categories are they're like wall contribution. I mean, they're associated to the codimension 1.
Not quite.
No.
Not quite, no. You can, if you do not ask for a universal skeleton, then you can build locally. Each time you do a wall crossing, you can build a window subcategory for that particular wall. But from one wall and another wall, they do not talk to each other, and there's no reason you can have a window category sitting at the original CN. So there's no particular reason that it can be true.
I mean, I think generally you do have, you have something, you have a family of categories over this hyperplane arrangement. Like you take the GKZ, like you take the GKZ fan and you sort of like shift it periodically, shift the walls periodically. You have hyperplane arrangement. And so there's a, there's a family of categories sort of like setting over this hyperplane arrangement where like generic fiber is like the generic sort of GIT mirror to the generic GIT quotient. And sort of like you can look at like how, you know, how things change when you hit the wall. And that's kind of the picture in my mind, but I don't really know what Peng has.
Right, so I was just saying in the special case of certain thing called a quasi-symmetric case, this is the case of the following thing. So suppose you have this Rn maps to Rk, right? And these basis vectors ei through en maps to some vectors on Rk. Let's call them beta 1 through beta n. They may be overlap and they may, there's, And then the quasi-symmetric condition is the following condition. It says, consider the lines generated by these betas. So there are finitely many lines connecting these beta. And then you want on each line to have a balanced condition. So sum of these beta i's lying on the line equals to 0. That is this quasi-symmetric condition. It's also equivalent to that. Yeah, I think that's the case. And in the end, you would end up with you can construct something called the window region, which is an intersection of some polytope with a lattice point in Rk. And those would correspond to, say, characters you want to put on characters of a line bundles you want to put on Cn. And those window subcategory generated by this line bundle have the property that they induce equivalences to all different quotients. And that's the case. That's indeed you have a universal skeleton. But in general, I don't see any hope.
So in this case, necessarily the GKZ fan is symmetric, I guess.
Well, okay, I guess we should thank Peng. Thank you. So thank you for giving this talk. If there are no more questions, okay. And maybe release the audience from.
Okay, thank you guys for listening.